As we continue our discussion of fluids, the other topic or another topic that's going to be important is the definition of pressure, and then specifically looking at the pressure of a fluid. So we start with a basic definition of pressure. So pressure is a way of describing that force can be distributed over an area, and that depending on how the force is distributed over an area, it can have a different impact. So in general, pressure is defined as force per unit area. So the units that we use, well, I guess first of all, the symbols that we use for pressure would be a capital P for pressure, force we use F, and then for area we use a capital A. So in general, we could talk about the pressure for a fluid, but we could also just talk about pressure in general. So this is a very basic definition. We could have a block sitting on a particular table, and based on the force that the block exerts on the table and the area of that particular block, there would be some pressure associated with it. So in terms of the units that we use, force in physics, the standard units would be newtons. And for area, we would use units of length times length, which would be meters times meters. So the standard unit would be meters squared. So the units for pressure would be newtons over meters squared, newtons per meter squared. And we define this as a new unit called a Pascal. So the standard units for pressure in physics would be a Pascal, which is equivalent to newtons per meter squared. So let's think a little bit about this idea of pressure. So we could think about the difference between the distribution of weight in a pair of tennis shoes versus a pair of high heel shoes. Which produces a greater pressure on the ground when a person is standing? So I realize that, we don't all wear high heel shoes. I actually don't wear high heel shoes. But in general, if you could imagine walking across, let's say, walking across a lawn, it's rained recently, so the ground is kind of soft. And so imagine someone walking across the lawn in their tennis shoes, right? Probably not really a problem. You might leave a little print on the ground from the tennis shoes. But imagine that same person putting on a pair of high heel shoes and walking across the ground. What can happen is that there's less cross-sectional area on a high heel shoe, right? You've got the pad of the foot that's got some contact with the ground, and then you have that heel at the end. So there's less cross-sectional area with the high heel shoe, which means there's a greater pressure. And so what can happen is that the heel of the high heel shoe can actually, go down and sink into the ground if it's a wet surface. And so the idea that the same amount of force is being applied on the ground in both cases of the tennis shoe and the high heel shoe, the pressure is different because the way that that weight or that force is distributed is very different based on the surface area. And so, again, maybe not everybody has the same idea of a high heel shoe, but you certainly get the basic idea behind this. If you've ever been with someone that's wearing high heel shoes and they accidentally stepped on your foot with the heel part of the shoe, it's going to hurt a whole lot more than if somebody stepped, with the heel of like their tennis shoe, right? So because of the fact that that force is distributed over a much smaller area, greater pressure. This is also relevant just in terms of the way that, animals are have evolved, I guess, over time. So an elephant has a foot pad that has a very large surface area, and that's because elephants are very heavy. And so you would want to be able to distribute that weight over a larger surface area for the same reason as the high heel shoe. As they're walking across a wet surface, you don't want them, they wouldn't want to sink down into the ground. They'd want to be able to stay on the top. So, so just an example of pressure here. This is not related to fluids, but it gives us a basic idea of what pressure is and how it's related to force and the surface area. What I didn't mention before is that pressure is a scalar quantity. It does not have direction associated with it. Of course, force has direction because it's a vector quantity, but the pressure is just a particular value. So, in terms of gases, it turns out that the gas that's in the air actually causes pressure on the surface of the Earth, or basically any place on the Earth, even if you are, up higher above the surface of the Earth. And the reason that we have pressure is because of the fact that if you think about a column of air, so here we have a picture, here's our city and here's our country setting, and then we have this really, really long column of air. And one of the things that we notice is that when we're close to the surface of the Earth, that the density of the air is greater than if we're really high up. It's much less dense. And so this long column of air actually has some weight associated with it. And that weight is above our heads, right? So if we were standing right here, we would have this long column of air above our heads, and it has weight and it's pushing down on us. So there is some force from that weight. And therefore, if there's force on a particular area, that means that there has to be pressure. So even though air is not very dense, it's very light in terms of a volume size of air is very light compared to a volume size of water, for example, it still is a very heavy weight coming down because that column that goes all the way up into the atmosphere is very long. So it turns out that if we were to look at 1 meter squared surface area on the ground, and we were to measure the column of air going up and figure out what is the weight of that column of air here in a volume, right? So this column of air has a particular volume because it's a cross-sectional area on the bottom of 1 meter by 1 meter, that we could weigh that air, and then we would know the area of the surface here, and we could measure the pressure. And what we would measure is that the pressure at sea level, this is an average value, is 101,000 Pascal. That seems like that's a pretty big number. So atmospheric pressure actually seems to be pretty big, and that's because that column is very long, and it's pretty heavy when you add up all that air that's in that column. The pressure does decrease with increased altitude, and it decreases by 1% for every 80 meters above sea level. So what does that mean? That means that if you're up here in that column of air, then the atmospheric pressure is less. Well, that should make sense because if we're here, we have less air above us pushing down. The other thing that you can keep in mind is that means that if you are in the mountains of Colorado, where you are higher in a higher altitude, atmospheric pressure is less. If you are at the base camp of Mount Everest, atmospheric pressure is even less. If you're at the top of Mount Everest, right, very low atmospheric pressure compared to sea level. So why is it that if we have this really large pressure that's pushing down on us when we are at the surface of the Earth, that we don't feel it? And the reason for that is because there's an equal amount of pressure inside our body so that we don't get crushed, right? So our body is equalized for the atmospheric pressure. And what happens is that if you change your pressure abruptly, then that obviously can have an impact. So one example of this is if you go very high up in altitude very quickly, it can cause problems inside your body. So mountain climbers, for example, have to climb high. It's called climb high, sleep low. So they might go up in altitude quite a lot, but then they come back down in altitude in order for their bodies to acclimatize to that decrease in pressure. So let's think about what's happening. So if you go up into the mountains and you go up very quickly, the pressure outside of your body is less, right? But your body is equalized for sea level pressure. So that means that you have a greater pressure inside your body from what you're used to at sea level. You go up high in the mountains, the pressure outside is less, and so you've got this pressure pushing out, right, from the inside of your body out. And so what can actually happen is because of that change in the pressure, you can have brain swelling and things like that when you go and you change your pressure too drastically. So if you've ever watched anything on mountain climbing, you would understand that they have this thing where they, especially Mount Everest, that you have to climb high and then come back down and sleep lower so that your body has time to adjust to that difference in pressure. So if somebody were sorry, I'm talking a lot here, but if somebody were to say, all right, well, I'm gonna go over to Mount Everest. I'm gonna start here in Virginia where we are, and I'm gonna take a plane over, and then I'm gonna take a helicopter, and I'm gonna be dropped off at the base camp of Mount Everest on a helicopter. Your body would go into basically shock, and your brain would swell because of the fact that you're not adapted to that pressure yet, and you would have all sorts of problems. So just an interesting aspect. I've actually been to the base camp of Mount Everest, and I've had to hike high in the mountains and then sleep low. So it's an interesting thing that you have to do. So a couple of examples of atmospheric pressure. If you've used a straw, everybody I'm sure has used a straw. What's happening is you're sucking the air out of the straw, and the reason that the liquid goes up in the straw is not really from you sucking. It's from the fact that when you pull the air out, the pressure in the straw is changing, and atmospheric pressure is pushing down on the liquid and pushing the liquid up into the straw. So a reduction here, you've reduced the pressure inside the straw by sucking the air out. Atmospheric pressure is still at the top, so it pushes the liquid up inside. So smaller pressure, and then of course atmospheric pressure pushing it up. Same thing is true here. I know as a kid I used to do this all the time. You stick your straw in your drink, and then you put your finger over the top, and then you pull the straw out, and the liquid stays in the straw. And that's because the top of the straw is no longer open to the atmosphere, and so some of the liquid might drain out a little bit, but then the rest of it will stay, and that's because there's a reduction in pressure here inside the straw, but the atmospheric pressure at the top is, or at the bottom of the straw, is still pushing up and holding that liquid in place. As soon as you take your finger off the top, atmospheric pressure is back at the top, and it allows the liquid to be released. So there's a lot of different demonstrations that you can see in terms of atmospheric pressure, just to see that it exists. I have a video link here for this thing called the Magdeburg spheres, and certainly you could take a look at that. This is a set of Magdeburg spheres. This actually comes apart right here, and you can pull it apart on either end. It has handles so that you can pull it, and then it has a valve. And so if inside there's actually air and outside there's air, you can just pull these two ends apart very easily. But if you connect this up, so that's the picture right here. The air pressure inside and outside the hemispheres are balanced, right? So there's the same pressure in and out. That's what the arrows represent here. So if you were to have one person grab on one end, another person grab on the other, and it does come apart in the center, they could easily pull it apart. But what happens is you can connect this up to a vacuum pump, and you can pull the air out from inside the center. So you suck out most of the air inside here. And one of the things that you would notice is that the arrows for the force have now become smaller. So atmospheric pressure is large outside. There's very little pressure inside. So the force, because the pressure is decreased, the force has decreased. So now you've got a lot of force on the outside, very little force on the inside. So if you try to pull these apart, it's going to be very difficult because there's this force that's keeping it together. And so it's a good example of how lower pressure inside here from the removal of air can have a big impact because atmospheric pressure is acting on the outside. So I would go ahead and take a look at that video if you have a chance, because it actually shows the demonstration for that. There's another number of other demonstrations that that can be viewed, and I'm just going to leave this page up for a second. But certainly, if you have a vacuum pump, you can suck the air out using a bell jar, and you can put different materials in the vacuum inside the bell jar and see what happens. For example, if you put a balloon in the bell jar and then you suck the air out, it will have an impact on what happens to the balloon. But again, these are great video demonstrations of atmospheric pressure and the impact that it has.